All right, to continue onward, we need to understand a relationship within coding. There exists a relationship between integers and their location on a 2D grid using both the mod function, which is also known as it's seen as a percentage, and just basic dividing. We can find, using these two mathematical functions, we can map out any integer into a 2D grid. Now, if you already know this, I can give a timestamp that will go to the actual coding, and you can skip over the explanation of what a mod function is. For those of you that don't know or don't understand this, I will now give an explanation. All right, so we have our grid. It's 4 by 4, and therefore we can map out any of these. We need to find where this exists in the context of a grid. Right now, it's just cell 5, but we can see here it's located at 1 1, or 11 is located at 3 2. And we want to we need that to, for example, spawn in tiles that we did in a previous video. Or if we're going to try to update neighbors, we need to find the tile that's above it or the tile that's to the right of it. And so we're going to use the mod. And this is usually represented as A mod B. In our example, A will be our cell index, one of these cells, and B will be the width of the graph. In this case, it is 4. And this can be said as there are 4 columns. It has a width of 4. There are 4 cells in a row. That means there's 4 columns. And so I might use those interchangeably. Okay. 4. Actually, let's pick a cell. We're going to do 11. So we're having 11 mod 4. Cell index 11, modulus 4, because there are 4 columns. All right, we have a width of 4. Now, what this actually does mathematically is it takes our number and just divides it. It divides A by B. And we can see here, just doing normal division, this goes in twice with a remainder of 3. Now this is where mod comes in clutch. This is the relationship right here, the remainder. So we see here that 11, if we come here, we actually see that it's located on the third x index, and that's exactly what the remainder is. And we'll find that we can divide any of these numbers by the width, and it will give us a remainder equal to its location on the x-axis. And then similarly, we see the whole product up here is actually equal to the z. Typically this is y, right? But in Unreal, we're going to refer to this as z. It will be equal to the z index. Right here is where 11 is located. So it's located at 3 2. It's located at 3 2. And that's perfect. And we could map any number. We could do the same with 13. So 13 divided by 4 will go in 3 times, which is 12, a remainder of 1. So we have our remainder, and we have our whole product, and we'll see for 13, it's located at 1, 3. That's exactly what that is. It is a remainder of 1 and 3. And that's where 13 is. So we can use this relationship to now interact with neighbors in a 2D grid with just integers that don't literally exist on a grid. But this mathematical function of using dividing and using the modulus will give us a way to actually find neighbors and perform bound checks, which is what we can now go straight into. Perfect. We've finished some math explanations. Let's hop into the coding. All right, so if you haven't watched previous two videos, please at least watch the macro video and the structures. It's macros and structures. I go over new macros and structures. I'll briefly cover them here because realistically, I know people won't start there. I created an enumerator called directions. It's got top, bottom, left, and right in it. I would keep it in that order. And I have a structure called tile set. It is type your tiles set to a set. Okay, so the first thing we need to do is get the number of entries and directions, -1, and go from the first index of 0 to that, which will be equal to 3. There's 4 options, so we need to go from 0 to 3. That will give us a loop of 4. The index needs to be converted to a byte. The byte needs to be converted to a directions enum. That's just done by searching directions, selecting that, and then promoting it to a local variable. Now we need to perform a bound check. We will use the direction wildcard, which I created and have provided in the macro library, to check that our cell, to check that the direction will be in bounds. We'll say it like that. So to know that the top direction of our cell will be in bounds, we're going to check the current cell index divided by the width of our chunk or our map, and then see if that is less than the height -1. And what that's doing is it's checking if we can check the top. So this will only be out of bounds if our cell index exists on one of these, because in that case, we'll see here, chunk Z -1, and my example, it's 4 tall, -1 is equal to 3, so that will give us this row being 3. If our cell's Z location, that's that relationship that we just went over, is dividing it by the width, that will give us the location in the Z axis. If that's less than 3 in this example, then we can perform a top check, because we know that we're not on this row. If we're on this top row right here, 12, 13, 14, 15, we don't need to check the top neighbors because they don't exist. There's nothing to check in the top direction. Now, that the inverse is true for bottom, we just need to check if we are greater than 0. If we are at 0, 1, 2, or 3, then we don't need to check the bottom neighbor because there's nothing here. There's nothing out there. And that's what this is doing. We're getting the current cell index, dividing it by the width, and that'll give us the location in the z-axis, and then we're checking to see if it's greater than 0. If it's greater than 0, that means we're somewhere in here, and so we can check the bottom neighbors. If we're in 13, we want to check that neighbor and we want to update it. If we're at 1, we don't want to. Okay, now for left, we need to see if our current cell index mod width is greater than 0. So what does that mean? We're getting where our cell is located, and we're making sure that it's not in this 0 column. Or if it is in the 0 column, we're not checking to the left. If it's, for example, over here, then we know that there is a cell that exists here, and we can perform the left update and check. If we are in the 0, then this is no longer true. 0 is not greater than 0, so we don't need to do a check, which is exactly what we want, because nothing exists out here. There would be nothing to check in the left direction. And then the inverse, or then for the right direction, we're just checking the same value coming out of the mod against the width -1. My example is 4 minus 1 is 3. So if our mod finds that we are in the third X column, then we don't want to do a right check because there is nothing out here. So we will not perform the check. If we're right here and we're maybe in cell 2, we do know that something will exist here. And so that bound check will allow for that. All right, next up, You can pull the out variable into a reroute node that's just done pulling off and pressing R. We'll use that in a second. The next thing we need to do is set the neighbor cell index. Now that we know it's within bounds in whatever given direction that we're currently checking, because this is swapping through all 4 directions, we need to check, or we need to actually set the cell index. We need to know what the neighbor is. If we've collapsed 0, the top neighbor will be 4. The right neighbor will be 1. We already know with our bound check that there will be nothing over here, so we will not be checking left or bottom. So to get from 0 to 4, we'll see here for top, we get the current cell index and add the chunk size. 0 plus the chunk size of 4 will get us to 4. 1 plus the chunk size of 4 will get us to 5. 10 plus the chunk size of 4 will get us to 14. And that will be our top neighbor every time. If we want to check the top neighbor of 2, we need to add the total number of cells in the width of the chunk or the map, and that will get us to 6. And this will work with any different sizes of chunk maps. If you have variable sizes, this will be consistent and always check the top because we're counting up. We're adding 4, we're adding 1, 2, 3, and now 4. That is always going to be the width, no matter how wide it is. Adding the width will always end us to the top neighbor. Now for the bottom, we just need to subtract that width. We need to do 13 minus the width of 4 in this example, giving us 1, 2, 3, 4, ending us at 9, being the bottom neighbor. And that will work for all cells and variable sizes. Now for the right and left, it is incredibly simple. To check in the left direction, we just need to get a cell like 1 and subtract 1. The left is directly to the left and the right is directly to the right, adding 1. And that's what that is. Left is current cell minus 1, current cell minus plus 1 for right. And we will promote the out variable to a local variable, and we'll call it neighbor cell index. And we're going to reference the neighbor cell index several times. So we need to now reference this and pull some information out about this neighbor cell. First thing we need to do is we need to actually find the neighbor cell in collapsed tiles. We need to see if it already exists. And in fact, we want to make sure it doesn't exist. If collapsed tiles already exist, if the neighbor cell already exists in collapsed tiles, that means it's already been collapsed. We are using this map to store all collapsed tiles. So we have right here, we're not going to look forward, we're just going to pay attention to this. We're checking an and. This and is making sure that if we follow this red, we are in bounds. That's what the out variable is. It's only true if we are in bounds and if the neighbor is not found, if it's not already collapsed. All right. So that's what this and is checking. And now we're doing a break and. We need to compare these two and do a few different things based on their results. Condition A, it's in bounds and it's not already collapsed. We did not find it. And it's in bounds. That's what this was. Secondly, condition B, tile options. This is a variable I covered in my macros and structures video. You can add it. It is key, integer, structure, tile set structure. And I explained this is where we store all tiles that are not collapsed, that have options, that have changed options. They can be something that isn't a high. It's okay. They can just be something. This is where we store the tiles that have options. So we're going to see if it exists. We're going to find it at the neighbor cell. And now we're going to compare. We're going to break apart that and, because this is a macro that contains an and inside of it, and it'll give us conditions. If both are true, if this and this are both true, we're going to do this. If this is true, but this is false, we're going to do this. And now what these two things are, if both of these are true, That means we found the neighbor cell index within our tile options map. That means there are options that already exist for this. What that literally means is we come into here as an example, we collapse this tile, we collapse this tile. Then when we want to collapse this tile, we're going to have to update this. But because this had already been collapsed, there were already tile options that existed for this specific cell. We have already updated it once, and now we need to update it again. And that's why we have the tile options. It's to find and contain these types of cells. It's to contain any neighbor cells that have already been updated. And so both are true. We need to set the set to a local variable. And now we're going to perform the macro create and check new tile options that I've provided. You can use the debug to give whatever function it is in. Currently, we are within collapse cell. We use this macro in several other functions, so this will allow us to know where things might be breaking. And then the debug cell is just the current cell indexed, just to know where things are breaking, like what individual cell. Now, what this does, as I showed in my maps, my structures and macros video, all this is doing, it's got some fancy things in here, but the core is it is performing an intersection between two sets. And what an intersection does is it finds values that are the same in two sets. And we need that because we need to know, based off of our rules, what can still exist for that neighbor cell. So we've collapsed this cell now. We now need to update this again because based off of the right rules, they may differ from the top rules from this cell. So we need to perform an intersection to find what is still equal and what can still exist here. An example may be that previously, without this, that cell could exist there. But now once we put that here, we can no longer place that cell here based on my tile rules. That does not function. So the intersection will clear that out and only allow things that can still exist there. It will be two options. It will be this and it will be this. Okay. And we have a few options for the out executes and out exec pins, and we just care about the new neighbor out for now. Invalid neighbors will deal with some of the more forward and backtracking logic, but we don't care about that yet. And the identical is a specific use case. This new neighbor options will give us that I just showed you there. It will give us those two options, the filled and this. And we need to add that to a local variable called neighbor options. We're not going to add it to the tile options yet, as we are uncertain if all of these cells, if all of the directions will work. In the previous video, I explained forward tracking and how we need to make sure that everything that our current option will be able to exist, that it can actually exist within the confines of its neighbors. So we're going to leave it in a local variable for now at the neighbor cell index. So it's still stored in the position, the place that we want it to be. And then if A is true, if we are in bounds and it's not already collapsed, but we do not find it within the tile options, then we know it's a case like this. It would be where we are just collapsing a cell for the first time, and now these two are being updated for the first time. They have no predisposed tile options. They have no rules that have been applied to them already. They are purely going to be based off of this one cell. It would be the same if we collapse that cell. Now this one, it's never been touched by any other cell. Same with this one. So we don't need to do an intersection or a check. We just need to, oh, that's right. Sorry, I didn't explain the rules. So I'll do that right now. We just need to add the rules to its cell index in the neighbor options local variable. Now, these rules are based off of our tile rule array, and we're going to get our selected tile, turn it into an integer, and then get that from the array, and that will directly pull the correct tile. If we were to say that we are using, still off of this example, the filled tile in my tile set, exists at index 1, and we can look over here that it is at index option 1, and we have our rules contained for top, bottom, left, and right. And that is, we're doing a select off of the direction. So all of these work in conjunction based off of direction to pull the directional information we need every single time. If we're working in top and it's past the bound check for top, we've gotten the top neighbor cell index, and now we're getting the top rules. So all of this works very fluidly with the directions. And I got a little distracted, but yeah, so we don't need to do this whole intersection check because we know that it was not already found. It has never existed before. This is the first time it is being updated. So we can just directly add the rules of the selected tile directly into that neighbor options map. All right. It's a lot of speaking. I've tried to add in examples and draw and demonstrate things. I hope it makes sense. The final thing I will do, I'm not going to explain this. I will just kind of go over this so you can see this is a debug. I'm using appends and formatting to let us actually see a cell's options. Perfect. Collapse. This is the right cell. And we'll see at cell 10, my current graph it's 10 by 10. My chunk is 10 wide by 10 tall. So this is cell 0. So the top neighbor, the only things inbound are the top and the right neighbor. Out of bounds is the left and the bottom because this is cell 0. So to the top of it, as this is 10 wide, will be cell index 10. To the right of it will be 1. We see top 10, ground 4, top right, ground 6, right. And that's exactly what can exist above this. It is my top right tile and it is my right tile. And to the right of it can be a blank and a top left and a left. And we could improve this a little bit. Let's actually improve this. How about we... No, I'm not going to improve this. This is fine. All right, so that's the debug, so you can kind of see what's going on. And that will be it for this current video. I hope that makes sense. That was a bit more in depth on some math and various bounds checks, variable checks, using ands, using my and macro, break and macro, and using some other macros. If you have any questions, as always, please feel free to ask. I'm here to answer questions. This is the most complicated so far. In the next video, we will take this neighbor options map and actually apply it to the tile options map. We will add whatever was in here as long as everything is worked out. Our forward checking has worked out. We can then add it to here. And remember, the distinct difference between these two is that this is all collapsed tiles. These are determined tiles. These are non-determined tiles. These are neighbors that have been updated but not determined. All right, that should be it for this video. This is a pretty long video, so please ask questions.